Why, welcome everyone to the, is it B1 Lecture Theatre? It's the Physics Department of Nottingham University, where I'm joined by a number of people. I said we'd start with a bang, that was more of a flash, but don't worry, there are some bangs to come. Because we've got so much to fit into this hour, I'm going to be very brief in any announcement I make. Firstly, there is an item on eBay which is being auctioned, which is writing on silicon. That auction finishes at 4:20 in 20 minutes' time, and the winning person will hopefully get to us the message that he wants written, and that will be written live during the course of this hour. Secondly, there's an update on the schedule. We'll be joined by Richard Dawkins at 6 o'clock this evening. That's 2 hours' time. And thirdly, oh yes, we are here to raise money for charity. Above the blog window, you will see a number of clickable links. Any case during the show, please click on them. They will open in a separate box. You won't miss a thing. But for now, I'm going to introduce you to Phil, who's going to talk you through what we're going to do in this hour. Phil.
Thank you, Richard. Very, very excited about this. It's going to be fraught, and let's hope the technology actually works. We're going to do a range of things. First of all, let me introduce my colleagues from chemistry, Dr. Pete Lysons and Dr. Darren Walsh. Right, tell us what this was like.
All right, so this was just a great experiment we thought we'd start off with, because we're using carbon dioxide here as a source of oxygen to burn a metal inside, and this is magnesium metal that we burnt inside. It makes a really lovely, really beautiful white flame, and inside here now, all we've got is magnesium oxide, and surprisingly, some carbon, because what's happened is the magnesium has reduced all of the carbon dioxide around it to make carbon. So you see inside here, we've got this lovely, lovely black carbon. It's still pretty hot, you know, but it's a great, great experiment of burning a metal in the absence of oxygen. What a fantastic experiment. So Darren's going to do an experiment now where he's going to use oxygen again, but like a lot more controlled way than we've done it here.
We'll pass over to Darren in a couple again while you're tidying up. So after Darren does his experiment, we're going to move over. We're in a physics department. We just could not avoid doing some experiments with the wonderful liquid nitrogen. And we've got Julian Sterling here, who's an excellent PhD student, who's going to be talking you through some liquid nitrogen demos. Then we're going to do, particularly because I know James Randy's been on the show and is going to be on the show, I hope.
Yes, later on.
So I thought I'd look at one of the classic telekinesis scams, which is the psi wheel, which some of you may have heard of, some of you mightn't have. And let's just talk a little bit about the physics of that. Then, as Richard said right at the start, we're going to write in very tiny letters, about 100 nanometers high, say about 30 to 50 atoms high. We're going to write a message that you tell us. And that'll happen round about 4:30. Then we're going to go and listen to some tunneling electrons. We're going to listen to quantum physics, basically. Then back to Darren and back to Pete to do some more chemistry. And perhaps then we're going to go to do some magnetic levitation to even levitate beer. And we're going to close with some music. I'll shut up, I've said more than enough. I'm going to turn back to Darren now, who's going to tell you about the next experiment.
Okay, so thanks, Bill. What I'm going to do is I'm going to do a oxidation reaction. I'm going to do a reaction that's happening, or happens in every one of you on a daily basis. And it's the combustion of sugar. So I'm going to react some sugar, everyday sugar, with oxygen. And my source of oxygen is actually a solid material called potassium chlorate. So it's potassium.
Here we go. We're on.
They're on.
We'll do it just so that one.
What? They can't hear us, right? I can't hear them.
I don't know. All right. Now, where's your time?
Say, I'm James Gould, and I'm with my colleague on stage, yeah?
That's the right correct. And then when you do it, present it to the camera.
Now in this case, we're going to be using a heavy piece of aluminium as a good conductor of electricity.
Maybe you could hold that next to it too.
Well, that's what we used before.
Right, but if, yes, hold it next to it to give you a relative size.
Well, I've got my hand there. You can see it. It's a heavy piece of aluminium there.
That'll be fine.
Yeah, so I can go down.
Well, I wonder if it's worth putting the stool.
Yeah, actually, put a stool there.
Move it back to sit down. You've got the window behind you. Right. Now then. I want to.
And I'm going to be talking here, so this is a heavy piece of aluminium. And then what I'm going to do is put this underneath the magnet as it drops down. Feel line penetrating this. I'm going to change. That change in the number of feel lines that penetrate the aluminium disc is going to induce a current. And that current over this large area will produce a powerful magnet effect.
See what I've done?
Oh, yeah.
Awesome. Right, so if I start out, I wonder if
How are we going to get, when are we going to get the prompt to start then?
I don't really.
You're going to sit down first, and then you get up.
Well, I wonder if I sit here and then you come in and sit there.
Let's get another chair,
stool?
yeah.
Okay.
There's one in there, I'm thinking, yeah, big magnet.
But it would be nice if we're both in
Yeah,
shot.
we're like a couple of pop singers, then we
Here's you need your mic off and Pete's back. So if you can get the mic off, just mute the mic. Sorry, no, it's just, it's
Remember to put it back on.
Okay. So you can see, it's a fantastic reaction. Look at all that energy that came out of about 50 grams of sugar. About the amount of sugar that's in a single Mars bar. Now obviously, this reaction, when you eat a Mars bar, you convert food into energy. You don't have flames shooting out of you. So nature does this reaction a lot more elegantly. And it involves the formation of proton gradients across membranes and the formation of ATP. But basically, it's the same reaction done quite quickly. Okay, so I'll hand back over to our host to see what's next.
Well, Philip's had to run away to tell someone to mute their microphone, but he's coming back now. Just in time to introduce Julian.
Well, I've just ran halfway across the department. Julian is very well versed in explaining the wonders of liquid nitrogen, and he's going to spend the next 5 minutes, 7 minutes, something like that, do some wonderful liquid nitrogen experiments.
Right, hello. So what I've got here is liquid nitrogen. So liquid nitrogen, famous from films where it flies across and freezes things instantly. It's exceptionally cold. It's minus 196 degrees C or 77 Kelvin. So first of all, some health and safety. Good idea not to throw it on your arm. Try not to throw it everywhere. So the reason why this doesn't, I got some on my t-shirt. The reason this isn't actually as dangerous as it looks is it's actually so cold that as it runs across the desk here, there's so much nitrogen gas evaporating straight away that it puts a protective cushion around me or the table, so I can put my hand in. As long as I don't leave my hand in enough for my hand to cool down, it won't actually quite make contact with me and I won't burn myself. So that's why most of the time I'm going to avoid wearing safety gloves because I just don't like them. So, I want to show you a balloon. So a balloon full of lots of air. If we take that air, we put it into liquid nitrogen. Now liquid nitrogen is just nitrogen gas. The nitrogen gas is about 700 times smaller when it's cooled down to a liquid. So if we put the balloon in there, we take the balloon out, and you can see that the balloon essentially looks empty. Now I haven't popped the balloon, all of the air is still in there, and if I blow on it, I can reinflate the balloon by blowing on the outside, which is probably the only time you can reinflate a balloon blowing on the outside. So a better demonstration of how much liquid nitrogen expands when you when it heats up is if I get this conical flask and fill with some liquid nitrogen.
It's dropped.
You can see that if I close the top,
It's dropped. Yeah. Yeah. So what's going on? If I dial in again.
Just leave it for now.
we're not live.
We are live. We're live.
Oh, we're live.
It's just that the
That's not live.
the close-up camera isn't live.
Good. Right. So I'm still meant to be doing things.
Yes.
Right. So this, if the liquid nitrogen, if we trap it, it will blow up the balloon. expands to 700 times the size. I'm going to need more nitrogen. I thought we weren't live, so I stopped talking. Right. So, however, if we enclose it so that it can't blow up the balloon, we end up building up pressure, and that pressure is turned into a force which can blow the cork out of the thing and up towards the ceiling. So I have one more experiment I quite like to do with things expanding, and I will need the close-up camera for it. Is it working?
Not yet.
Not just yet. Think of something else to do.
Think of something else. So things
Pulling you back
sometimes
in
expand very rapidly. Whoa! That wasn't meant to happen.
Okay, we're back in, Jimmy.
Well, something else. So what I've got is just a normal, very little. I've got something. Thank you.
You might.
You had sticky goggles, and I did. So I've got normal fairy liquid here, just fairy liquid and some very hot water. We throw in liquid nitrogen. It expands very quickly, quicker than I thought, and we end up with lots of bubbles, lots of very big bubbles, all filled with nitrogen gas. We cover Phil's laptop, and
It's creeping. It's like a 50s movie.
yeah, so there's no scientific purpose to showing you this. It's more just because it looks like, yeah, a 1950s horror film. So the close-up camera's working again.
The close-up camera's working, yes.
Right, so if we cut to the close-up camera, what I have is no liquid nitrogen now.
Can't see. It needs to pick it up a bit.
Yeah, you're going to bring it over here, aren't you?
Yeah.
Yeah.
So what I've got is this one or this one?
This one.
We're on this one.
This one.
So currently I've just got a ping pong ball here, a normal ping pong ball, and if we put that in the liquid nitrogen, we'd expect it to crumple down and go very small, just like the balloon did. However, I've punctured two very small holes which you won't be able to see in it, and this allows me to completely fill it up with liquid nitrogen. So I'm not sure if you can see, I've just got...
Yeah, hang on.
I've got the ping pong ball being held into the dewar.
Yeah.
It's being completely filled up with liquid nitrogen here.
Yeah, just about see it.
Okay, and if we put the camera back down so we can get it towards the desk. So what I'm going to do is I'm going to put it down.
Right.
And the liquid nitrogen is going to start to heat up. It's going to swell up to 700 times the size and be forced out of the ping pong ball. So, can you see that?
Yeah, we can see your hands. Ah, it's gone. Where's it gone? Bring it back. Where's it gone? Yeah, there we go. There we go.
And it works a bit like a jet
Where's
engine.
it gone? Hi.
And it's actually a very fast jet engine, very simple jet engine, just from heating up the liquid nitrogen, forces it out of the two holes which are at slight angle, and it spins around exceptionally fast. It's the exact same design of a steam engine that was invented in the 1st century AD by Hero of Greece, who used a copper ball, I think it was copper, may have been brass, and filled it with water because he didn't have liquid nitrogen, and put a flame underneath and got them to spin round. But unfortunately, sorry, it's Hero of Alexandria, I got told off for that. But back then, they didn't bother to use steam engines to power anything, and instead just used it as a fun desk toy. So can I cut back to the main camera? Do I have any more time?
No, you're gone. You're gone. Right.
So I understand that we're back on, and I think we've had some technical difficulties here in the physics department, which have led to us losing all of our connections. So I'm terribly sorry if you didn't get to see our superconducting magnet levitating the flying saucer, because frankly that's rather cool. So we're setting up some magnetic experiments behind me. There's all sorts of chaos going on here, and then I'm going to show you some of the more classical mechanics type experiments that I was due to be doing in about half an hour, but apparently I'm being brought forward. Okay. Are you ready?
Right, yes.
I'm going to hand over then.
So this is a novelty, because I'm a chemist, and now I'm going to tell you something about magnetics. Maybe. Okay, so we've just seen some great experiments by our friends about some cryogenic liquids, particularly this one here, liquid nitrogen, yeah? Now me as a chemist, this is a really boring compound, yeah? Because, well, it doesn't really react, it's very inert. We use it to stop chemistry going crazy, yeah? It provides an inert atmosphere. If we think about the structure of nitrogen, yeah, the dinitrogen molecule's got this amazingly strong triple bond, and the electrons in that triple bond are all paired up All right. So we think about it. There's no unpaired electrons in that structure. It shouldn't be magnetic. It should be pretty boring, and it describes its reactivity. So let's do a physics type experiment, yeah? Because if there's no unpaired electrons, i.e. they're all paired, it shouldn't act like a magnet. So let's have a look. This is a very expensive piece of improvised equipment. This is the Nottingham University's magnetometer. I think we'll call it the octopus. It's a bit like a squid, but not quite as elegant, all right? So let's fill up our sample container. All right, so there's some liquid nitrogen going in there, cooling down this really elegant sample holder, which is called a test tube, okay? There we have our liquid nitrogen. All of those lovely paired electrons. Now then, like all types of spectroscopy, I've got to poke my molecules. It's a bit like poking a crocodile with a stick. Well, look at the reaction. So the poke is a magnet, a real proper magnet. Now then, if there's unpaired electrons in that sample, it will be attracted to my magnet. If there's paired electrons in there, it won't. It will just sit there and smile and laugh at me. So let's have a look. Here's a magnet, big magnet, no reaction. Definitely no unpaired electrons. Now then, we came across to the physics department this morning, Darren and me, with our liquefied gases, and the physicists got their liquid nitrogen out, and we said, that's not fun, let's get another one out. This is liquid oxygen. It's a bit different. Okay, so this oxygen gas, which has been liquefied by our chemical Stig, Neil, he's a superstar, okay? Now then, the difference between the structure of liquid nitrogen and liquid oxygen is in the bonding. And in the bonding of liquid oxygen, some of those electrons are unpaired. So they will react with a magnetic field, okay? And similarly, they're also coloured. So we'll try for a close-up here. If you look into my dewar, hopefully you'll see it's a lovely blue coloured solution. Okay, you can see it in there, nice, lovely blue. Now most chemists, when they see the blue of liquid oxygen in their reactions, absolutely panic, because they're very reactive, those unpaired electrons, and they tend to go bang with things. But first, I've got to prove to you it's got some unpaired electrons. So I'm going to fill it up into my squid magnetometer, or sorry, my octopus magnetometer, and I'm going to see if there's any unpaired electrons. So here we are. Here's our tube. Let's fill it up with oxygen. Okay. Now, unlike liquid nitrogen, liquid oxygen sticks to your hands. It's really nasty stuff, and it does burn quite badly. So there it is, and you can see the lovely blue colour behind all that nice frozen out water from the atmosphere. Now if I take my magnet, let's see what happens. I can see that it's attracted into the magnet, and I can pull it a long way. You know, fantastic. There's a big difference between them gases, and if I was in the chemistry department, I'd show you some real chemical reasons too, because I could do some fantastic things with biscuits and cotton wool and all sorts of other non-reactive things. And in a minute, I'm going to show you a reaction of the oxygen with a really frighteningly reactive material, phosphorus. But before I can do that, I'm rather hoping Darren's got something to do now so that I can catch a bit of breath.
Okay, so
Going to react some gases, yeah?
What I'm going to do is, we saw earlier on that we saw some liquid nitrogen blowing some bubbles in some soapy water. So I'm going to do a very similar reaction, except I'm not going to use nitrogen because, as Pete just said, nitrogen is a little bit boring. I'm going to use butane. So I have a bucket of soapy water here, and I'm going to blow some bubbles. I hope you can see me there. I'm going to blow some bubbles that I've filled with butane. Okay? So you can see, getting some bubbles going here. Hope you can see that. So it looks very similar to the liquid nitrogen case. Remember, we made those bubbles filled with nitrogen. But we've got, in this case, bubbles filled with butane. Now the really nice thing about butane is it's flammable, right? So we're the chemists of the bunch. We like playing with flammable things. You see, we've got a lot of nice bubbles here. So we're going to see, I can just hand this off to my glamorous assistant. Thank you. I get my torch, and we're going to see, can we get these butane bubbles? So if I can take a handful here, we can see, get them go on the table. Got some bubbles. Now these should be filled with my butane. I'm going to see, can we combust the butane within the bubbles? So you can see, extremely nice reaction. Okay? A handful of bubbles, all filled with butane. Get it to react with oxygen. I get my match in. This is my start the reaction, my activation. You can see a really nice reaction. So bubbles that go on fire. And I think that's pretty cool.
Can I step in here? There is no way to describe how smoky and how smelly it is getting in this lecture theatre. Any minute now, these guys are going to set off the fire alarm. We're having a brilliant time. It's all improvised. I'm back over again.
Right. So, we're still having technical difficulties, so we're now going to go right to the end of the show and bring in back some more chemistry, which we were really going to try and finish with. So we've got a couple of reactions, which again, looking at really, really reactive things, and we're going to see if we can sort of get a bit of a sparkle or something different out of it, okay? So let's have a look. Now over here, I got a flask. It's just a small flask. It's something I might use in the laboratories. And what I'm going to do is I'm going to burn a really reactive element in there. So I'm going to take some phosphorus. This is P4. It's the sort of stuff that's put in awful weapons, and you know, it's a precursor for big chemical reactions. It's very reactive. It's 4 atoms that are sort of brought together like a tetrahedron, and those bonds between the atoms are really, really strained, and they just want to rip open and really, really sort of burst alive and do some chemical reactions. But I want to burn the phosphorus in an oxygen-rich atmosphere, okay? Now, the atmosphere that we're all breathing here is 19, 20, well, probably about 18% oxygen now, because we put a lot of CO2 out there earlier, yeah? So, but there's not enough oxygen in that atmosphere to sort of start this combustion with the phosphorus. So what I want to do is I want to kick out all of that horrible inert nitrogen from inside this flask. So I'm going to go back to my favourite friend over here again, which is my liquid oxygen, and I'm going to pour some in here to displace all of the nitrogen from that experiment. Okay, so here we have this lovely blue, here we go again, lovely blue, frighteningly reactive oxygen. And I'm going to throw some into my flask. Oh, fantastic, there you go. Put it on the top and let all that evaporate so that we don't have to flash it all off. Okay, so there's liquid oxygen in.
Right, we're back live.
Okay, we're back. Thank you for coming back. I'm sorry we're having such serious technical problems. Hopefully the science won't let us down. This is my favourite reaction. It's one of my favourites because it always works. You know what's going to happen now, don't you? Anyway, before we were rudely disrupted by the bin men, okay, we filled this flask with oxygen. So now I just need to make sure there's none of that horrible nitrogen got back in there. So I'm going to do my favourite experiment ever. And it is the first experiment I ever did in science, which is to relight a glowing splint. This is a lit splint. This is a glowing splint. It's now relit. Fantastic, that's the power of oxygen. So, we've got oxygen in there. Now what we want to do is we want to put something very, very reactive in there so that we can burn it really, really quickly and see how nice the flame is, okay? So let's go now. So here I have a small vessel which has got a lot of water in it, because inside that vessel there's a small piece of phosphorus. Now if I come closer to the camera, you can probably see a really quite nice piece of glassy white phosphorus. Now what I'm going to do is I'm going to pitch it in there and I'm going to give it a little bit of heat. That's the heat that Darren told you about earlier, the activation energy. And we're going to see if we can get it to react. I'd love to turn the lights off for this reaction, but the whole system is dead and it won't allow me even to do that. So, here comes the phosphorus, being careful not to drop it on the floor, because a fire in the physics department now would not be very good. And in she goes. Oh, I need a bit more light. So, my phosphorus is in there, it's very, very reactive, it's full up in that oxygen-rich atmosphere. Now all I need to do is warm it up a little bit. Can I have the lights off now, please? So this is a copper bar, and I'm just warming it up so that I can actually just touch my phosphorus and see what happens, okay? So let's go fishing for phosphorus in my big vessel. Wow, fantastic. There she blows. All of that phosphorus is reacting with all of that oxygen now to make phosphorus pentoxide, which is a hygroscopic material. It reacts with the air and the water, and it forms this fantastic white smoky stuff, okay? Now what we're seeing is the burning of the phosphorus, but also phosphorescence, which is like some funky maths type stuff, and it's really, really nice. It's like a secondary emission of light. What it means, though, is that it's very cold. It's not very hot. In fact, it's probably where the luminescent light came from in our kitchen, but I'm not saying that you want to make it using phosphorus and liquid oxygen, okay? Brilliant experiment. Let's do another one. Are we back?
Do the magnets?
Yeah.
Right.
Do a magnet.
So it's time to do some magnets.
Well, thank you very much, guys, for some truly impressive improvisation there. We promised you some magnets shortly before everything went terribly wrong. I am now happy to say that I'm ready to deliver some magnets for you. They're all over there, so I'm going to go and get them and drag them into the one part of the stage which is actually working. Okay, so I'll be back in a moment. Okay, so I believe that when we went off, I was talking about a copper pipe. Now, the thing about a copper pipe is that it's not magnetic. But when I drop a little magnetic plug, can you see the magnetic plug? When I drop that through the pipe, as you can see, it falls really, really slowly. The reason that it falls slowly, well, your first guess might be something to do with air resistance. But I've got here a non-magnetic plug, and when I drop that through, that goes through quite quickly, so it's certainly not air resistant. And actually what's happening here is something that Michael Faraday first noticed back in the 1830s, is that when you move a magnet close to a conductor, you generate a current. So maybe you remember this from high school, Fleming's left-hand rule. What that means is that a moving magnet with a magnetic field pointing in this direction, that's towards the camera, will generate a current going in a circle in this direction. And that current has got to have a magnetic field of its own. That's on this hand, right? And that magnetic field's got to do one of two things. It's either going to repel the falling magnet, in which case the magnet gets pushed along by the new magnetic field and it gets to move faster and faster and faster. And as it moves faster, it generates a bigger and bigger current, and that repels the magnet faster and faster, and very quickly the whole universe disappears in a little puff of infinity, which, you know, as a physicist, I don't like that very much. Or the magnetic field must push back against the magnet, and that's what it's doing. So we're generating a magnetic field, and it's pushing the magnet back up the pipe and slowing it down as it falls. Okay, I have some other little magnetic treats for you. I'm back. Now what I've got here, there's a wonderful thing in magnetism. You've probably all tried at some point to take a North Pole magnet and balance it on another North Pole magnet. Any of you who haven't tried that completely lack scientific curiosity, okay? But I'm guessing that probably none of you have ever succeeded, and the reason for that is because it's impossible, okay? What you can't do is balance a North Pole magnet on a North Pole magnet and levitate stuff, okay? But now, having said that, I'm going to try and show you some levitations. I have no idea how well these are going to come over on the camera. What I've got here is just a little spinning top, and I can spin that, and maybe you can see, I hope you can see, that that's levitating. Okay, but I just told you that it's not possible to levitate one magnet on top of another. So what's happening here? Well, I hate to admit it, but I'm cheating. I'm cheating by having a small glass plate just here. If I remove that, whoops, then we're back to a position where it's completely impossible to levitate one magnet on top of another. Okay, it'll just fall over. So this is an executive toy. It's not really magnetic levitation at all. So enough of that. Let's have some proper levitation. Now I can't tell you how difficult this is. What I've got here is a large lump of magnet, and I've got a spinning top. Now when you spin a spinning top, it stays horizontal. And the reason it stays horizontal is because you've given it lots of angular momentum in the horizontal plane. And nature can't just create and destroy angular momentum. So once it's got it, it wants to keep it. So if it tilts over like this, then that's trying to create angular momentum in the vertical direction. And that just, it doesn't want to do that. Okay, so that's what keeps the top the right way up. Now if I put that with a magnet, and I'm going to give it a little spin, and I've got a suspicion this isn't going to come over well, but I'm going to try anyway. I give it a spin. Oops, better than that. And then if I just lift that slightly, you see that stabilizes. There it is. And then, oh, well, it's pretty close. What's happening here is that there's a force pushing the magnet down. That's called gravity. Okay, if we didn't have gravity, then we'd all be floating around. It'd be a lot more fun, but it's probably, on the whole, it's a good thing. Right, so there's a force pushing it down. There's the angular momentum keeping it horizontal, but there's a force pushing it up, and that's the repulsion between the two magnets, which you can see is what's going to flip that over. So you can buy one of these in, Christmas gift type shops. Probably get one on Amazon or something. And you can spend many happy hours levitating magnets, and it's actually possible to make that levitate for 1 or 2 minutes. We've got a video which does that on the 60 symbols, so I really recommend going to take a look at that. Right, what other magnetic toys do I have? Well, what I've got here is a very small chunk of superconductor. Now the thing about superconductors, and you'd never have guessed, is they conduct incredibly well. They're superb at it, right? Now what that means is that if I drop a magnet, that's very kind of you, Julian. We'll have some of that. Go on. Now first things first, superconductors only work when they're cooled down to very, very cold temperatures. In this case, liquid nitrogen, about 60 degrees Kelvin. Okay, so we can hear that boiling away. That's the superconductor cooling down. Now when I drop a magnet close to a superconductor, just the same as the magnet dropped in the pipe that I originally did, it tries to generate a current, okay? But that current, well, the conductor's so good that the current is trying to make it infinity. But we don't like infinities, so obviously something else has to happen. And what happens is that all the current is trapped in the surface of the superconductor, and you end up with its own magnetic field pointing right back at the falling magnet. So wherever the magnet falls, there's a magnetic mirror of itself pointing back. And what that means is that this tiny little magnet, and I really hope I can get this on the screen. I can't see the screen, so I have no idea what you can see.
Up a bit.
Up a bit.
Up a bit.
Up a bit, yeah.
Yeah, there you
Right.
go.
Tilted.
So I'm going to take this tiny little piece of magnet and I'm going to drop it onto the superconductor. And hopefully you can see there that wherever that magnet falls,
And then tilt the camera down.
wherever that magnet falls there we are.
That's it, good.
It's going to levitate directly above the superconductor. And this is how things like magnetic levitation in trains works and so on. They always have a superconductor and then a magnet falling on top of it. And that will levitate there essentially until this magnet warms up and stops being a superconductor again. Okay, so that's all the magnetic toys that I'm able to bring.
I have one.
We have one more.
Julian has one, yeah.
You got the train track.
We'll come back to that. Right.
Let's go to Julian.
We'll go to Julian. We're going to hand over to Julian, who's got something fancy.
What I have here, if you can see it, I'll just put some other things out the way, is I have a big coil of wire. This big coil of wire is plugged directly into a plug. So if we plug it into the mains, it will try and draw 100 amps. It's going to try and draw 100 amps going around in this way, which will blow the fuse. But in that time, as all of this current spins around, it will make a really big magnetic field. Now, if I have some aluminium on here, this magnetic field, just as James said, will produce an electric field which will cause electrons to rush around this block of aluminium. And that will produce another magnet. And just as with the copper pipe, they will repel each other, but this time it will go shooting down the lab. So I'm just going to cool it down to liquid nitrogen temperature because it will conduct much better at liquid nitrogen temperature. And I'm going to hope that I remember to put a new fuse in it. And when I flick the switch, what should happen, are we ready? Is it goes flying down the lab. And so that's just very, very quickly, current spins around when we plug it in, magnet produces another magnet here, goes flying off down the lab and makes a disturbing whirring sound that is never used. And that's my magnetic cannon. I think James has a racetrack now for you.
I do, but I need it to be a little bit higher at one end. So, hello again. I'm just going to find something to prop one end of the racetrack up. Don't you mind what?
Seems right, nice.
If it'll hold it. Right, we're improvising left, right and centre here.
It's a smoking racetrack.
Right. Now then. In a minute, I'm going to ask you a question, and I'm going to leave it for you as a brain teaser. So this is just as by way of a warm-up. What I've got here is pretty much the first thing that you see when somebody introduces you to physics. So I've got a ball, and I'm going to sit it on the track. Can we see that?
Yep.
I'm going to sit that on the track, and it's got some potential energy because it's higher than the bottom of the track. But when I let it go, it turns that potential energy into kinetic energy, and then it goes back up the other side and turns it back into potential energy again. This is very simple, sort of physics 101 concepts. Okay, now the next thing I want to do is put a second ball in the middle of the track. And now I'm going to do the same thing, and what should happen here is that all of the energy of the first ball, all of the kinetic energy that the first ball has, is transferred into the second ball, and the second ball goes off up the track. And I can keep doing that, and you might recognize this as a Newton's cradle. So I drop the ball, and the ball on the far side goes off up the track. And it's not as good as a Newton's cradle because there's oodles of damping in this experiment, so too much friction, really. Now what I want to do is introduce a magnet, because this section is all about magnetism. So I'm going to go back to my magnet, which has attracted all sorts of other little bits of random metal. And I'm going to introduce my magnet into the middle of the Newton's cradle. Okay. Whoops. So that's the magnet in the middle of the Newton's cradle. And that's me falling over the microphone. And I'm going to drop the ball. And of course the whole system's dead, right? Because the magnet's attracting all of those balls. But this is where it gets fun. These are strong magnets. If I make that asymmetric, so now all the balls are on one side, and now I'm going to drop the second ball in, and what happens is we get loads of energy coming out the other side. So what's going on? Well, what's happening here is that as the ball falls, it's attracted towards this magnet. And that attraction makes this ball accelerate into the collision. So it gains loads of energy as it's coming into the collision. And when it collides, it's coupled mechanically through the magnet and through 1, 2, 3, 4 new balls, and it sends the last ball shooting out with all of that extra energy that it's gained. What's important here is that this last ball is much further away from the magnet, so it's much less strongly attracted into that magnet than the first one. So the asymmetry in the setup is causing us to shoot that second ball out really quickly. I'm going to show you that one more time. Here we go. This is called a Gauss cannon, by the way. By all means, make one at home. You can get a magnet like this out of your parents' stereo system. Don't use your own stereo. And off it goes. Excellent. Right. I like that. Now then, I have one question, and then I'm going to leave. I'm going to hand you back over to Pete. Pete, I guess? Right, good.
Quickly.
And that question is, I've got two balls that are basically identical, and I have two racetracks. Now, one of them has got much less of a slope than the other. If I kick off both balls with the same amount of energy, which one will get to the other side first? Okay? One of them has got a long way to go, but it can gain loads of speed as it goes down the slope. The other one hasn't got very far to go at all, because there's much less of a bend on the track, but it doesn't get to gain much speed because there's no slope. Okay, I'm going to answer that question for you in about 10 minutes.
Or it'll be less than that.
Less than that. Right, who's next?
Kate, quickly, bring your tube down. So Darren and I have got one last experiment which we wanted to show you. And this is a mad experiment. We call it the barking dog, yeah? And there's a question for the physicists in there, because there's two breeds of dog. The one Darren's got over there is a Chihuahua, and the one I've got is, I suppose it's an English Bull Terrier or something like that. And they've both got two different pitches to their bark, and we really don't understand why, because we're just simply silly. But what we got here is an N2O, laughing gas, okay? It's a carbon disulfide. It smells of rotten cabbage, it's really rank. We've mixed them up, now we're going to set them on fire. So we pop these down in. Where's the torch gone, guys?
I need some wool paper in there.
Okay, just pop it down.
You okay? Yeah.
Good lad. Okay, so here's our mixture. So we got N2O, which has got lots of oxygen,
carbon disulfide, lots of carbon. So we've got fuel, oxygen. Now we need some light. Yeah, we need bigger energy. So down something like that. Fantastic. Here we go. So it's a bit like synchronized swimming at this time of the day, and we're all sinking. So ready? 1, 2, 3. Thank you very much.
Yes.
So please answer on the back of the postcard to the pitch.
Do you want to give
I'll do that, yeah.
You want to do that, yeah? Right. Okay, so can you set it up so we sit here? This will be quite quick. I'm going to try to get the chair over here. Yeah, we'll have to do a complete dual. Right, to close up, well, first of all, apologies that things didn't exactly go to plan. It looks like sort of Hades in here. It's smoky and smelly due to the chemists. But I hope you've got something out of it. I hope you've enjoyed aspects. I'm really sorry. I guess we were just a little bit too ambitious, but we've had problems with audiovisual systems and internet, etc., etc., etc. We're going to finish, not quite finish. Richard's going to close up the hour. But at least in terms of the people here from Nottingham, we're going to finish off with a bit of music. This is a piece which is based around fundamental constants. We've taken something called the golden ratio, and also something called tau, which is 2 pi, which some of you might be familiar with, and also aspects of Fibonacci sequence, or Fibonacci series, which is some of you might be, again, familiar with, and we've generated a piece of music based around those. If you're interested, I'm very happy for you to email me or contact me via Richard, and, well, let's just play it. It goes something like this. Thank you. Back to Richard.
Oh, no, we're going to have to go back to the ball bearings.
Oh, we are indeed first.
Well,
10 minutes ago, I asked you a question, and the question was, if I release 2 balls on the racetrack, which one is going to make it to the far end first? And the answer, of course, is the bottom one. I should leave you to do the maths. It's quite an interesting problem. One for the back and then one afternoon. Our chemistry friends asked us a question about which, or why the pitch of the 2 different explosions was different. What may not have been obvious to you on the camera, it's a little bit more obvious from here, is that the 2 pipes are a different width, and I suspect that that's there. All right, I shall hand you back to Richard. Thank you very much for joining us at Nottingham University. We've had a great time, even if it has been complete anarchy. And have a good day.
Can I just echo my thanks to everyone that's taken part today? And you've probably not seen them all. There are 7, 8 people being involved in it. And I haven't got time to go into detail, but the winner of the writing on silicon we already have, it's already been done. Unfortunately, we wanted to show it you live, but we weren't able to. I will show you that image later when I get back home. But I've got the rush now. Because in less than an hour's time, just less than an hour's time, I'll be joined by Richard Dawkins. So I've got the shift on. See you in an hour. Thanks very much, Tony. If you want to end it there, the next hour it will be Together for Peace and Religious Antagonists. Enjoy.